This is section 13.6, and this is example 2. So we're going to evaluate this surface integral where the surface S is the hemisphere, x squared plus y squared plus z squared equals 4, and z is positive. So what we're going to do is we're going to start with, because we don't have this yet, we're going to start with a vector equation for the surface. So right now the surface is in rectangular form, x, y, and z, and so we're going to put this in spherical form. So we'll let phi and theta be our variables. And if you remember from spherical coordinates, the x coordinate is going to be the radius, which is 2, times sine of phi times cosine theta, and then y is 2 sine of phi times sine theta, and then z is 2 cosine phi. And then while we're at it, let's go ahead and do our partial derivatives of this. So we have our partial of phi, which is going to be 2 cosine phi cosine theta, and 2 cosine phi sine theta, and then negative 2 sine phi. And then we have the partial with respect to theta, which is going to be negative 2 sine phi sine theta, 2 sine phi cosine theta, and 0. Okay, you can already start to see this problem is going to be sort of lengthy, but then let's go ahead and tackle the cross product of these two partial derivatives. So we have the partial with respect to phi crossed with the partial with respect to theta. I'm going to pause and set this up. Okay, so I've just substituted in my vectors here, gotten it all sort of set up. Let's go ahead and start to calculate this. So we have 0 and then minus a negative. So we have a positive 4 sine squared phi cosine theta for our first component. Then our second will have 0, and then let's see, then minus, and we have to multiply by negative 1. So we're going to have positive 4 sine squared phi sine theta. And then for our last one, you can't really simplify much. It'll be 4 cosine phi sine phi cosine squared theta minus a negative, so plus 4 sine phi cosine phi and sine squared theta. Okay, so really ugly one. Now if we look at this third component, if you think about it, what we could do is factor out a 4 cosine phi sine phi. What we're left with is cosine squared of theta plus sine squared theta, which is just 1. So it will help us, I believe, if we do simplify that. So we can't do much with this one. Can't do much with the second one. However, the third one, we get 4 cosine phi sine phi. So it looks a little better. Not a great deal better, but a little better. Okay, now you already know what's going to happen here. We're going to do the magnitude of this. So the magnitude of this cross product is going to be pretty ugly as well. But you also probably suspect this will simplify. And if you do, then you're right. So we have the square root of, let's see, 16 sine to the 4th phi cosine squared theta plus 16 sine to the 4th phi sine squared theta plus 16 cosine squared phi sine squared phi. All right, let's see if we can simplify that down a little bit. So remember, when we look at the first two components here, they share a 16 sine to the 4th phi. If we factor that out, we get cosine squared theta plus sine squared theta, which is 1. So in other words, this could be simplified to 16 sine to the 4th phi. Remember, we factored that out, and so the cosine squared sine squared theta cancels to 1. And then we have plus 16 cosine squared phi sine squared phi. we're going to sort of do the same thing here. We're going to factor out a 16 sine squared phi from both of these terms. And if we do that, we get a sine squared phi and a plus cosine squared phi left over, which is also 1. So in other words, this simplifies again to 16 sine squared phi. And believe it or not, we finally have a reduced cross product. So 4 sine phi. Okay, our next step is probably to set up our function. And remember, we set up an equation for our surface. Our equation was up here, the vector r, and what we're going to do is we're going to take x, which is 2 sine phi cosine theta. We're going to put that in for x, and then for z, we'll put in 2 cosine phi, and so on. So we're going to substitute back in for our function up there. So our function of x, y, and z is going to turn into the function of r of phi theta. So what we get then is 4 sine squared phi cosine squared theta. That would be x times z, which is 2 cosine phi, plus 4 times sine squared theta sine squared phi sine squared theta. That would be y squared, and then we have times z again. So we have times 2 cosine phi. So again, I'm taking this is x squared, this is z, this is y squared, and then that one is z again. So we're just taking our function of x, y, and z, we're just changing it into the parameters we've set forth. Okay, I think it makes some sense to simplify this. We don't really want to do an antiderivative yet. So what we get is 8 sine squared phi cosine squared phi. Sine squared phi cosine to the first phi cosine squared theta plus 8 sine squared phi cosine phi and then sine squared theta. And if you notice, we can do the same kind of thing we were just doing in the black just above, is that we're going to factor out all of this stuff, and what we get is cosine squared theta plus sine squared theta, and that is 1. So what we get for a reduced function is 8 sine squared phi cosine phi. So that's our function. Okay, I think we are finally ready to set up our integral. Now remember, the way that we're going to calculate our integral is that we're going to, let's just make this, we'll do theta. So in this particular case, if we have the top half of a sphere, theta is 0 to 2 pi, and phi would be 0 to pi over 2. Remember, if it was an entire sphere, it would be 0 to 2 pi and then 0 to pi, but we're just doing half of that. Okay, then what we have is our function, which is 8 sine squared phi cosine phi multiplied by what we got for the cross product, and then we wrote it as d phi d theta. Okay, so there's our double integral finally. I think maybe one last step here. Let's do 8 times 4, pull that out to the front. So we have 0 to 2 pi, and then we could do d theta times 0 to pi over 2 of sine to the third now phi cosine phi. Okay, I think we are finally ready to calculate this. So now it's all old stuff, and the best way to do this is to do a little u sub for this integral. So you have u equal to sine phi and du equal to cosine phi d phi, and that gives you then the integral of u cubed du, which is 1/4 u to the 4th. All right, so what we have then is 32. That comes from the front, and then we have this integral, which is just 2 pi. So 32 times 2 pi times, and then we have our 1/4 u is sine of phi, and we're evaluating from 0 to pi over 2. And sine of pi over 2 is just 1, so what we get is 32 times 2 pi times 1/4, and that gives us 16 pi. So that is our final answer, and that is example 2. So in the next video, we will continue to move through section 13.6.